Okay, catalysis. So we learned that we can control the rate of a chemical reaction or affect it by changing the concentrations and by changing the temperature. Both of those have limits. You can only go to a certain high concentration. Once you get to a pure substance, you can't get it more concentrated. And you can't have something operating at a temperature where the molecules decompose. You can't have, maybe there's a reaction in your body that would work really well at 50 degrees Celsius, but your body's at 37 degrees Celsius. And so you can't have just one part at 50, so that reaction goes nice. So the third thing is a catalyst. Catalyst increases the rate of a reaction without being consumed. So however much catalyst you start with, you still have the catalyst at the end. The catalyst is like a helper that's providing a different mechanism for that rate limiting step, a different mechanism that has a lower activation energy. Decomposition of ozone again. So the uncatalyzed reaction occurs by a single elementary step. The activation energy is so high that this rate is pretty slow. So the ozone layer does not just rapidly decompose into O2. This is a good thing. But chlorine atoms act as a catalyst. They provide another pathway. So when chlorine atoms are present, you can get this different pathway that has a lower activation energy, which means the rate will go faster. Does that make sense? Is the chlorine actually in the chemical equation? No, it's just a catalyst. It provides the alternate mechanism. So here's the mechanism for catalytic destruction of ozone by chlorine. Chlorine atom reacts with ozone to make ClO and oxygen. This is an intermediate. The ClO then reacts with an oxygen atom to make Cl and O2. So here, the catalyst is present in the first elementary step as a reactant. It's used, and then it's released in the last step. So that there's a difference between an intermediate and a catalyst. The catalyst is going to show up as a reactant and get used in some way and then get reproduced. That's different than ClO, which is an intermediate. This gets formed in the first reaction and gets consumed in the second reaction. Both of them cancel out and don't show in the overall chemical equation. Let's just show how that works. So we've got chlorine on each side, and we've got ClO on each side. And so we end up with this overall equation. You could be given this mechanism and asked, what species is the catalyst? So you're looking for something that was there to start with and is there to end with. The intermediate is something that you didn't start with. It shows up in the middle, and then it goes away again. So the catalyst is not consumed in the overall reaction. Where do those chlorine atoms come from? Photodissociation of man-made chlorofluorocarbons. So, we used to put Freon in our air conditioning units, and Freon contains chlorine and fluorine, and it gets up into the atmosphere, and then the sun, energy from the sun causes it to dissociate and release fluorine atoms and chlorine atoms. And then those can catalyze the destruction of ozone. So the ozone layer is getting thinner, and they're like, what's going on? And then they figured it out, and so they passed rules, and It's taken a while, but it's finally having an effect, and the ozone layer is getting healthier again. Yeah.
What did you mean by what species is the catalyst?
Okay, so a species is just a thing. It's an atom, a molecule, an ion. It's a chemical thing, right?
And in this case,
The chlorine is the catalyst. And we identify that because we see that we start with it and end with it. It cancels out, it doesn't show up in the overall reaction. The intermediate also cancels out. But the difference is you form the intermediate and then destroy it. The catalyst gets used or destroyed and then reformed. I haven't heard this on the news recently, but catalytic converters are a great target for thieves. On the bottom of your car, easy to steal, and they've got valuable metals in them. What is a catalytic converter? Well, it's got a solid like platinum, rhodium, or palladium. These are rare metals, valuable. That will be on a high surface area substrate. And as the exhaust pollutants, such as NO and CO, come past that, the metal catalyzes a reaction, lowers the activation energy, so that these guys are going to react and form nitrogen and CO2. Well, nitrogen is completely harmless. Most of the air is nitrogen. The air also contains CO2. Now, too much CO2 is not a good thing, but this is not a toxic, harmful chemical, okay? It is associated with global warming, but forming some CO2 here is much better than having these guys running around. It also helps with the complete combustion of fuel fragments. So your fuel is going to be hydrocarbons, carbons and hydrogens, and when it burns, it doesn't all necessarily burn. It should form H2O and CO2, right? That's what a combustion forms. How does it form? No. In that reaction, sometimes nitrogen from the air participates and gets involved, and that's where the NO comes from. So this catalyzes it back to the original nitrogen. You're not supposed to be involved in this, get out. Any questions? A couple different kinds of catalysis. We can divide it into homogeneous or heterogeneous. And here we're looking at what states are the reactants and the catalyst in. So homogeneous, the catalyst is in the same phase, the same physical state as the reactants. So an example of homogeneous catalysis would be the chlorine catalyzing the deconstruction or the destruction of ozone. Everything's in the gas state, they're all in the same state. Heterogeneous means that the catalyst is in a different phase than the reactants. So a catalytic converter is an example of that. The catalyst is a solid and the reactants are gases. There is a big old hole in the ozone that appears over Antarctica every year, and then it disappears again. Next year, shows up and disappears. Heterogeneous catalysis is most likely responsible for the formation of that. Say most likely, right? Because we can't prove it.
Does it only happen in September?
It only happens, it's called the Arctic Spring. So Antarctica is on the other side, and so when we have winter, they have summer, and when we have fall, they have spring. And it happens in the spring down there, which is going to be September, October-ish. So what's going on here? Well, Chlorine is evenly distributed throughout the entire atmosphere. Those chlorofluorocarbons have gone everywhere, they spread out, it's equal. So that doesn't explain why this hole would form in one place. Something different has to be happening here. Turns out that the chlorine atoms from the chlorofluorocarbons get bound up in substances such as ClONO2. So it gets tangled up with oxygen and nitrogen, and this compound cannot catalyze the destruction of ozone. The single chlorine atom by itself can. So this kind of thing is what's saving the ozone layer, right? If we didn't have the chlorine getting bound up like that, all of the ozone would have been gone a long time ago, because the catalyst never gets used up. It just keeps going and going, and it's just going to destroy everything. So there are clouds that have ice particles in them. The ice particles catalyze reactions that release the chlorine. So here's that thing where chlorine was bound up, and it can get released as molecular chlorine. In the Antarctic spring, there's more sunshine, and the sunlight dissociates those chlorine molecules into chlorine atoms. Those chlorine atoms catalyze the destruction of the ozone. And so this is going to continue until the stratospheric clouds melt. Ozone hole appears every spring and lasts 6 to 8 weeks. It all has to do with ice particles in the clouds. Interesting, huh? Yeah.
What does it mean to dissociate?
Dissociate, come apart. So a chlorine molecule is two chlorine atoms bound together. And to dissociate means the chlorine atoms come apart from each other. Any other questions? Another example of catalysis is the hydrogenation of double bonds. Ethene has a double bond between the carbons, and you can react it with hydrogen and have one hydrogen add to each carbon and get ethane. But that's pretty slow at normal temperatures. If you have a catalyst, again, a finely divided metal such as platinum, palladium, or nickel, that reaction will happen rapidly. And the way that it catalyzes it, the thing that's holding this up is that the hydrogen-hydrogen bond is very strong. So with the catalyst, the hydrogen molecule sticks onto the catalyst, and that tweaks its bond and weakens it, which makes it easier for the reaction to occur. Hence, it's faster. I forgot to tell the other classes, why do we even care about this? Have you heard of partially hydrogenated vegetable oil? How do they hydrogenate it? Like this. Why would they want to do that? The double bonds are going to affect the properties of the fat or the oil. More double bonds, it's going to be affect the melting point the most. So having lots of double bonds, you're going to have, I believe, a lower melting point. So this is going to be like a liquid at room temperature. Whereas once it's hydrogenated or partially hydrogenated, it might be a solid. And so they take an oil that maybe is cheap to get, but it doesn't have quite the right qualities. And so they partially hydrogenate it to make it what they want. There are 4 steps of heterogeneous catalysis. I'm not going to test you on these vigorously. The first is you get adsorption. So the reactants have to adsorb, they have to stick to the metal surface. Then we get diffusion, where they're going to move around on that surface, which seems kind of crazy, but they do. And then you'll get a reaction where the reactants react, and then desorption, which is the opposite of adsorption, when they come off. There might be questions on the practice quiz about that. And I'll just tell you also that sometimes I put questions on the practice quiz that I would never think of putting on the final exam. I mean, on the actual exam. Because I figure the process of figuring them out for the practice quiz is good enough. So, yeah. Question?
Why is it adsorption, not absorption?
That's a good question. Absorption and adsorption are two different things. And just off the top of my head, I think the difference is that adsorbed means it's just on the surface, whereas absorbed means it goes into it. So you could get absorbed into a liquid, or a porous solid could absorb water, but this would just stick on the top. Yeah, good question. Anybody else? Many of you know a lot more about biology than I do. I was never a fan of biology. I took it as a sophomore in high school. I had to take a life science for my chemistry major. Horticulture 101. I learned how to propagate houseplants and fertilize the lawn. Actually, a lot more practical, I think. Anyway, but parts of biology, especially the biochemistry, I find fascinating. So, organisms have all these chemical reactions that need to occur. And they're too slow under normal conditions. And you can't just heat the organism up because you're going to kill it doing that. So how do you manage this? How do we stay alive? Enzymes. Enzymes are biological catalysts. They're usually large protein molecules. So the reactant molecule, whatever's reacting, is called the substrate. And that's going to stick to the activation site, bind to it, and it does that through intermolecular forces, like hydrogen bonding and dipole-dipole forces. And when it does that, it greatly lowers the activation energy of the reaction. So this is the general idea. The enzyme plus the substrate. So the substrate sticks to the enzyme. Now we have this complex. And then a reaction's going to occur, and the products leave, and the enzyme remains. The enzyme is a catalyst. It's involved, but it doesn't get used up. So it catalyzes one reaction. As soon as that one's over, hey, bring in another substrate. I'll help you out, and it just keeps going and going and going. They work because this active site is very, very specific. A lot of them are specific for one molecule. And if you've learned about chirality, things like sugars have a right-hand version and a left-hand version, and a lot of these are specific for one or the other. So like in drugs, you have two forms of the drug, a D form and an L form, and only one of them will be active because only one fits in the active sites. Very, very interesting. Okay, so let's look at the digestion of sugar. So sugar is sucrose, and sucrose is glucose and fructose connected by a single bond here. Your body needs to break this to release the glucose and fructose so it can do other stuff with it. Well, this bond is pretty strong, and so at normal temperatures, this is a really slow reaction. Your body needs it to happen faster. So the enzyme, sucrase, and it's not a coincidence that the enzyme name is like the sugar, the substrate. So sucrase, if it ends in ASE, that's the enzyme. And sucrose is what it works on. So when this binds in here, it binds in such a way that it kind of stresses that bond. And because it's stressed, it's weaker, and it breaks easier. Any questions? enzymes give organisms tremendous control. You think about all the chemical reactions happening in your body, and I mean, just like the release of adrenaline when you're threatened. Well, that reaction is always potentially available to you. Why isn't it going all the time? How does your body control that? It uses enzymes, right? So most of the reactions are too slow unless the enzyme is there. So your body makes the enzyme that catalyzes the reaction, speeds it up, and produces adrenaline, and then you run away screaming. Their enzymes are very specific. They each catalyze a single reaction. They speed up the rates by factors as large as 1 billion. This is not twice as fast or 3 times as fast. This is 100, 1,000, 1,000,000, 1 billion times faster. Crazy. There are substances that can inhibit enzymes. Those can be very toxic in even small quantities because that substance may bind to the active site and just stick there. And that puts that enzyme out of commission, right? It can't catalyze the reactions. So locking up one enzyme molecule can prevent the reaction of billions of substrate molecules.